Okay, Advanced Algebra Trig. Today we're going to take a look at graphing the cosecant and secant functions. What we're going to do here is we're going to go through and we're going to graph functions as if they were sine and cosine. The first one's always a little confusing, but I think after you get through that one you'll be able to look back at it and it'll make a little bit more sense. So let's jump right into example 1. So for example 1, I would like to accurately graph the function f of x is equal to the cosecant of 1/2 x. Now a couple FYIs to go along with the cosecant function. Again, I know you have absolutely no idea what this thing is going to look like, but the cosecant function does not have amplitude. Neither will the secant function. Let me say that again. Cosecant and secant do not have an amplitude. The only functions that you graph in trigonometry that have amplitude are sine and cosine. However, the period for cosecant, since it is a reciprocal of sine, so on a side note, remember that cosecant of x implies 1 over the sine of x. So we know that they are very tightly connected. Their graphs will be somewhat similar, and we're going to use that to our benefit. So the very first thing that we're going to do is we're going to state the period of this. Just like before, the same thing works. The general period for cosecant is 2 pi. But we're going to divide that by the coefficient on the x term. If we divide by 1/2, again, that's the same thing as multiplying by its reciprocal. So we know that the period of this function will be equal to 4 pi. Now the process that we did before with putting the function equal to 0, putting the angular measurement, this part right here, equal to 0 and equal to 2 pi still hold true. So if we consider one cycle, we know that it will start when our expression, angular expression here, which is 1/2 x, is equal to 0, and it will go until, or terminate, when that angular measurement, which is 1/2 x, is equal to 2 pi. So notice this is identical to drawing the sine function. If I solve each of these linear equations, we find that x is equal to 0, and it will terminate when x, well, I guess we should go ahead and multiply through by 2. That would be solving the equation. So when x is equal to 4 pi. So what we have here are our start and stop. I'm going to go ahead and highlight that because it's one of the most important parts to this entire problem. Next up on the agenda is to construct a t-table. So on our t-table, again, XY table, and I'm not going to bore you with some of the basic things of separating this into 4 different intervals. We've been practicing this a lot. I know that it will start at 0 and it will terminate at 4 pi. Obviously between that would be 2 pi and between that pi, so we're very easily counting by pi's. Now, when we get our actual outputs for y, what we're going to be doing is we're going to consider the equation y equals the sine of 1/2 x. Notice the similarities here, ladies and gentlemen. This is almost identical to this. They're just written as reciprocals. We'll go into further investigation in later examples as to why things are working the way they are. So what we're going to do is we're going to think of taking this 0 and we're going to plug it into this sine function. Very easily, the sine of 0 is 0, so we still get that coordinate. If I take pi and I plug it in here, the sine of pi over 2 is clearly 1. If I plug 2 pi in, 2 pi over 2 is pi. The sine of pi gives us 0. If I plug 3 pi in there, I'm going to come up with -1. and if I plug 4 pi in there, I'm going to come up with 0. I know I'm moving quickly with that aspect, but it's expected at this point that you have mastered graphing sine and cosine functions. Now the next thing is we're going to plot these points, and we're essentially going to play dumb. We're going to graph it as if it's a sine function. So I'm going to go ahead and draw my xy axis over here. And your y-axis on these typically needs to be a little bit larger. So on the x-axis, I'm counting by pi's. So pi, 2 pi, 3 pi, 4 pi, 5 pi. I have more than what I need, but for our first example, I want to make sure that you're seeing the big picture of everything that's going on. And for our y-axis, I'll put a couple tick marks on there. Let's go to -2 to +2. Now before you start actually graphing the sine, I want you to know that we are going to erase, let me say that again, we are going to erase the graph of the sine function at the very end of this. So don't go and write super hard or write in pen, because it will not be part of the actual graph. So I'm going to use, let's use green, since we're actually graphing the sine function here. And I know that I'm going to have a mark, let's see, at 0, 0, so I'll put a dot there, and then pi comma 1, and so forth. Now obviously I can't draw lightly, so I'm going to go to a finer tip pen, and I'll have to erase this later on. So generally speaking, and it doesn't have to be pretty because I'm going to erase the darn thing anyways. Generally speaking, we know that the sine, again, the sine of 1/2 x will look like that green curve there. But that is not our actual graph. Now let's take a look at what we're supposed to graph. Now everything that we're going to, all of these coordinates on this first one, you have to keep in mind that what we're really looking at is the reciprocal of what we have. We're not really graphing y equals the sine of 1/2 x. What we really want is y equals 1 over the sine of 1/2 x, because that is equivalent to the cosecant of 1/2 x. Again, I know this is not an easy idea to grasp, especially on your first one. Essentially what this is saying is that we are going to take the reciprocal of the outputs that we were able to get. Now, as you saw in the unit circle of the cosecant function, if I think of the cosecant of theta, it's undefined at those locations. What's important here is there are some places where the cosecant is undefined. That means that we will have vertical asymptotes. Remember, an asymptote is an imaginary boundary that a graph approaches, gets infinitesimally close to, but does not cross. These asymptotes will always occur at those places of equilibrium. So it's right in the middle of the graph. I'm putting purple asterisks on them right now. So there would also be one over here at 6 pi. All we have to do there is put a vertical asymptote. So I'm going to put a dotted line that passes through those. Now the next thing is these peaks, this peak, this trough, and every corresponding peak and trough, they are always part of the cosecant function. They're part of these reciprocal functions. So we get to include those. So I'm going to make those a little bit heavier. They are going to be part of our actual graph. Now, since this is advanced algebra, generally I'm just going to have you draw what I always say are the horseshoes. We'll investigate why the numbers are what they are. this picture is generally going to look like this. So it's going to sweep up, and then it goes down. And then it sweeps up on this other one, and this goes on forever, this up and down process. Notice that it is cyclic. You get an up horseshoe, you get an asymptote, then you get a down horseshoe, then another asymptote, and then it repeats itself. The distance from here to here is 4 pi, which is what we knew from the very beginning, that it would be 4 pi. The stuff we have in purple here is our graph of the cosecant of 1/2 x. So at this point, all we need to do is erase the green. So I go through with my pencil and lightly erase all of that. That part that I just erased in green must be removed from the graph. That, ladies and gentlemen, is the graph of the cosecant function. So for example 2, see on the first one we took a look at cosecant. Why don't we change gears here, and this time we're going to look at the secant function. So example 2. We are going to accurately graph y equals 2 times the secant of the angle x plus 2. So for all those students that are looking at this in terms of shortcuts, we know that what's going to happen is this is going to, the factor of 2 on front is going to change the amplitude of the cosine function. So it's going to stretch it vertically, but then we are also going to have a vertical shift up 2 units as well. All right, so just as always, there is no amplitude on the actual function. What we are going to look at is finding our starting and our ending points. There isn't much of an equation to solve on this one, so we would say that it's going to start when our angle x is equal to 0, right? Not much to solve. We've got it. It's going to finish its cycle when x is equal to 2 pi. Again, not much to solve here. So we can quickly knock out a t-table, x comma y. Starts at 0, goes to 2 pi. And you've memorized these values on the unit circle. Lightning fast here. It's what's in between, pi. If we split that in half, we get pi over 2, and then we get 3 pi over 2. And I'm not going to bore you with a lot of this stuff. You've been through it many, many times. So again, in the back of my head, I'm keeping in mind that this is kind of like y equals 2 times the cosine of x plus 2. Now be careful, be extremely careful. If I take 0 and I plug 0 in, cosine of 0 is 1. 1 times 2 is 2. 2 plus 2 is 4. So we get the coordinate 0, comma 4. Pi over 2. The cosine of pi over 2 is 0. 0 times 2 is 0. 0 plus 2 gives us 2. Pi is up. Cosine of pi is negative 1. Negative 1 times 2 is negative 2. Negative 2 plus 2 gives us 0. 3 pi over 2. Cosine of 3 pi over 2 is 0. Times 2 is 0. Plus 2 gives us 2. If we plug 2 pi in there, clearly we end up with 4 once again. Let's get our quick xy axis. Now, sometimes it pays to step back and look at your values. Look at the y values here, ladies and gentlemen. Every y value is positive. We're not going to need a lot of stuff that's below in quadrant 3 and 4. So I'm going to choose to make my graph look like this. Now I know that the majority of the stuff I'm going to have to erase, so just going to put real little circles. We'll go ahead and throw one more on there. Should be right about here. I'm going to lightly trace my graph. It's going to look something like this. I'm going to switch colors so that we can see what the actual reciprocal function will look like. Now this is the tricky part with this problem. I like to go after my asymptotes first and foremost. The asymptotes are going to happen right here, and right here, and right here that I just crossed an X in purple. Notice they are in the middle of the sinusoidal. In my first video I talked about this being a wave in the middle of the ocean. If I could calm this ocean down, where would the water settle? Where would the water settle? And clearly it's going to happen on those purple X's. And that's the first thing I go after. So I'm going to go ahead and draw my asymptotes in. Notice how easy this is once you have the sine or the cosine graph in. So I have my maxes and my mins. I've got a dot that's located right here. It's generally speaking going to go from here to here. And then from this one, it's going to move upward. And I'm going to go ahead and show a little bit of one more cycle. It's going to go in this direction and up over here. And I'll erase the red. And so the purple there, you have a general sketch of what 2 secant x plus 2 would look like. Now I want to talk about two elements that I didn't do in the first problem. That's describing what the domain and range is. The domain on this one we're going to leave pre-calculus class. It's a little more complex, but I would want you to understand how to write the range of this function. So in the bottom left-hand corner, I'll show you. If I wanted you to tell me what the range of this function is, again, we know that it starts, how far down does it go? It goes forever. So it starts at negative infinity, and I will have y values all the way up to 0, including 0, so I'll use a square bracket. And then union, I'm going to have another interval that I have to talk about, and its range goes from 4 to positive infinity. Again, 4 is included, so I use a square bracket. So if I asked you for the range of this function, that is one way to present it. The last thing that I'd like to brush on is kind of an FYI, just for extra information. Why does this graph look the way that it does? And I think this makes the most sense when you look back at the original function we did on example 1. What I would like for you to consider is, what if we plugged in a value at an x value that was very, very close to 2 pi, but not quite 2 pi? If this was the original sinusoidal function, it would have looked something like this. So when you plugged in a value, you had an output that was maybe, I don't know, 1/5 high. So again, it would correspond to being 1/5 above the x-axis. Remember that in the red, we're actually graphing the sine function, but that's what we used with the red portion. What we are really interested in is the cosecant function. And so what you're really plotting is the reciprocal of 1/5. And the reciprocal of 1/5 is 5. And that kind of makes sense on why in the reciprocal part of it, it approaches this asymptote and is much, much higher. You can then imagine that if I went even closer to this place that it's crossing at 2 pi, that maybe I have a corresponding y value of 1/100th. Again, its reciprocal would be 100, and so its output would explode and lie very much off our particular graph. So I hope these two examples of graphing reciprocal trig functions helped you. Thank you.